A differential equation is actually something we've looked at before, because we've looked at equations like this. Y prime equals 2x. Now keeping in mind that y prime means the derivative of y, that's what makes this a differential equation. A differential equation is simply an equation that has derivatives in it. If we're asked to solve a differential equation, what we'd like to do is rewrite this equation so that instead of knowing what y prime equals, we know what y equals. Now that's also something that we've done before, because what we can do is find the antiderivative of both sides of this equation in order to find a solution for y. You'll notice that the equation has that plus c in it, that arbitrary constant. That's also something that's not new to us. And we know that if we have information about how x and y are related to each other, we might be able to find a value for c. We'll look at that in just a little bit. Here's a differential equation that we're asked to solve. And we also have an initial condition, which is f of 0 equals 8. Because we have an initial condition, we'll be able to figure out a value for c in this equation. But let's solve it first and find a general solution. So if we take the antiderivative of both sides of the equation, we can find an equation for y, which is that y equals e to the x plus 5/2 x squared minus 2/3 x to the 3/2 plus c. That's our general solution. In order to find a value for c, we can use our initial condition, which is when x is 0, y is 8. So if we substitute 0 for all of our x's and 8 for our y, and then solve for c, we'll find out that c equals 7. And substituting that in our general solution for c, we get what's called the particular solution of this equation. If what we've just done looks familiar to you, it is because we've done this before. We have solved equations before when we knew an antiderivative, and we found a value for that arbitrary constant c when we knew an initial condition. We're just calling it something different this time. We're calling the derivative that we're starting with a differential equation. We're calling the antiderivative of that a general solution. And we're calling the equation that we get when we substitute the values for the initial condition in and find a value for c, we're calling that the particular solution. So now let's see if we can prove that we have found a solution to a differential equation. Now first of all, let's think about the notation here. Y equals 4e to the x plus 5e to the 3x is an equation which describes a value for y. We want to show that that's a solution of another equation. And the other equation not only has a y in it, it has a y prime, which means the derivative of y, and a y double prime, which means the second derivative of y. So we're going to have to find the first and second derivatives in order to see if we really do have a solution. So let's start by finding the first derivative. So if y is 4e to the x plus 5e to the 3x, the derivative of that is 4e to the x plus 15e to the 3x. Now we need a second derivative, so we'll take a derivative of that equation. And we'll get the second derivative is 4e to the x plus 45e to the 3x. Now it's time to do a little substitution. Everywhere in the equation where we see a y double prime, we'll substitute 4e to the x plus 45e to the 3x. And where we see a y prime, we'll substitute 4e to the x plus 15e to the 3x. And that gives us this. Now we've got some algebra to do. We'll distribute the negative 4 and we'll distribute the 3, and we get this. Now let's look for some like terms. First of all, the terms that contain e to the x. We have 4e to the x minus 16e to the x plus 12e to the x. Well, that equals 0. And now the terms with e to the 3x in them. 45e to the 3x minus 60e to the 3x plus 15e to the 3x. And all of that adds up to 0 as well. So we get the equation 0 equals 0, which is a true statement. So if we can substitute for our derivatives, for our y prime and our y double prime, and in doing so we get a 0 equals 0, then we can say that we have indeed found a solution to our differential equation. Let's solve this differential equation. Now it may look a little different than the others did, just because we have a notational difference. You'll notice that this equation contains dy over dx, which is the same thing as the derivative y, or y prime. So we do have an equation that involves a derivative. It is a differential equation. Now to solve it, the first thing we're going to do is called separating the variables. That means anything that has a y in it, whether it's a y or a dy, we'll keep that on one side of the equation. And anything that has an x in it, whether it's an x or a dx, we'll move to the other side of the equation. So we'll start by subtracting x from both sides of the equation. And then we'll multiply both sides of the equation by dx. So now everything that contains a y or a dy is on the left side of the equation, and everything that contains an x or a dx is on the right side. So we're ready to integrate both sides to find the antiderivative of both sides of this equation. The antiderivative of 3y squared dy is y cubed, and the antiderivative of negative x dx is negative x squared over 2 plus c. Now technically we do get a plus c on both sides of the equation, but we're just choosing to combine both of those arbitrary constants into one constant on the right side of the equation. Now solving this equation means we would like this to say y equals, not y cubed equals. So what we'll do is take the cube root of both sides of the equation, and we'll have y equals the cube root of c minus x squared over 2. Now we're not quite done, because we have an initial condition. We know that y is 5 when x is 0. That's going to let us figure out a value for c. We'll substitute 0 for x and 5 for y in our equation. And then we'll simplify, and we'll get 5 equals the cube root of c. So we'll cube both sides, and we'll get c equals 125. So the particular solution of this equation is y equals the cube root of 125 minus x squared over 2. It's the solution of the equation when we have an initial condition, initial values for x and y, which allow us to find a value for the c. One last differential equation to solve. Now this one looks fairly simple. Y prime equals x squared y. We're going to approach it the same way as the other one. We're going to separate our variables. But before we do that, let's change our notation just a little bit. We know that y prime means the derivative of y, so that's the derivative of y with respect to x. And we're going to do that because we want to get everything that has a y or a dy on one side of the equation, and everything that has an x or a dx on the other side of the equation. So we'll divide both sides by y, or multiply by 1 over y, and we'll multiply both sides by x. And now that we've got our variables separated, we can find the antiderivative of both sides of the equation. And we'll have the natural log of y equals 1/3 x cubed plus c. Now remember, we want to figure out a value for y, not the natural log of y. So we have to use our properties of logs to rewrite our natural log equation as an exponential equation. So that means y equals e raised to the power of x cubed over 3 plus c. Now be really careful here. The plus c is up in the exponent on the e. Now one last thing to do to simplify. One of the properties of exponents says that a to the m times a to the n equals a to the m plus n. So if our bases are the same and we're multiplying, we can add the exponents. We're going to take that property in reverse, because on the right side of the equation, we have a base that in its exponent has a sum. So we're going to pull that apart on the right side, using the property of exponents, and say that the right side is the same thing as e to the x cubed over 3 times e to the c. Now the only reason we're doing this is that e to the c is e, which is a constant, raised to a constant. So e to the c is really just another constant. So we can write this as y equals our new constant, which we'll just call c sub 1, times e to the x cubed over 3. That's our general solution. It looks a little different than we're used to seeing general solutions look, because the c in this case isn't added. We're used to seeing a plus c on the end of our equations. In this case, the c is multiplying the e to the power.